Hello, everyone, and welcome to the recorded content of the Hacking Exposed Live Mobile Targeted Threats webcast. In an effort to minimize the amount of time needed to view this session, we've shortened the recorded content down to just the main topic areas. For full slides and a direct link to the Android exploit demo, please visit hackingexposed7.com. I'll now turn it over to Georg to get started.
Hello, my name is Georg and I'm a senior security researcher with CrowdStrike, and I'm going to walk you through advanced mobile targeted threats today. So the outline of this talk is also the threat evolution that we observed. It all started out with commercial raids back in around 2006, and those were basically primitive raids that were manually installed on a phone and had this spy on your girlfriend type of idea. So it was mainly marketed to the consumer market. And from that, it went to simple targeted raids that we see in the real world. And those are simple, regular apps that are being used by threat actors to target specific targets. But from a technical standpoint, they're not very sophisticated. And then from there, I'm going to go to the advanced threats that we see both being out there today with a very limited visibility, and also thinking about what are we not seeing. We put together a case study how feasible it is to create something very advanced, and I'm going to walk you through that as well. So to start things off, what is a RAT? And a RAT is just short for Remote Access Tool or Trojan. And it's basically a post-exploitation tool in that you first gain access to a system, either by physical means or by an exploit or social engineering. And then once you gain the access, you want to maintain the control over the system and therefore install a RAT. So it basically gives you persistence in the system. It allows you to exfiltrate data and carry out your attack further instead of just gaining access in the first place. And this has been done for normal desktop computers or PCs for a long time, for many years. And what these programs basically do is they have different capabilities to allow an attacker to gather data, like activating video cameras and microphones on a computer to actually gather what's going on in the physical surrounding of an affected computer, take screenshots or pictures of the remote system, which is a very, very easy generic way of identifying what the user is currently doing on the computer. And then classical data exfiltration by sending out files, which makes it more efficient to look at documents because you can then actually search for content and so on. As well as run remote commands, which can be used for anything like advanced exfiltration or allowing lateral movement within a target network and so on. And of course, logging of keystrokes, which is interesting to gather keyboard input, which can lead to harvesting of passwords or other interesting information. So as I said before, those threats have been around for a long time. And it all started with programs like Orifice and NetBus, which have all kinds of functionality, even prank-like functionality like opening CD-ROM drive and so on, but also allowing to actually get information from the computer, like taking screenshots and exfiltrating data, gathering passwords, and so on and so on. And so what is emerging right now is basically transforming this kind of program to the mobile ecosystem, because in the end, mobiles are just computers that are very small and that you carry around with you that carry a wealth of information on them too. You have your email on there, documents, and so on and so on. So a movement of these threats to the mobile system is just natural progression as people start moving the data onto mobiles as well. And we're starting to see this in the wild. As I've said, since 2006, maybe there has been these commercial raids that need to be placed on a phone manually by the attacker. So you require physical access to the target device. And not only that, but you even need to know the target's password or PIN number if there's any configured. So you cannot just walk to a device and if it's locked, install it. You actually need to unlock it. And then you have to install it from actually a third-party market or a web page. So it's not even seamless in text. If you're looking at an iOS device, you even require a jailbreak for the device, which usually requires hooking up the device with a cable to a laptop, but also restarting it and so on and so on. So this is really where you see that this is targeted at the consumer market, where people have this information about maybe their partner that they want to spy on, or similar cases. One specific example is FlexiSpy, that has all these, properties that I just discussed. And from the capability standpoint, basically what FlexiSpy allows you is monitoring email that is being received or sent by the phone, monitoring SMS and MMS messages, so everything that's being texted with the phone. It has support for some specific applications like Facebook or WhatsApp, and it also allows flagging of numbers that are being dialed. And this is interesting in combination with the call interception. So if there's a call going on live, you are actually able to listen in. But you're not only able to listen in on one-way calls, but also using the hot mic functionality, you can actually listen in what's happening around the phone right now. So it basically is like turning the phone into a bug. And then as a backup channel, besides normal TCP/IP communication, it can also be controlled over text messages if there's currently no data network available. This is an example of what FlexiSpy looks like from a user perspective. This is the web interface, and you reach this web interface by going to the FlexiSpy website. So basically this means you're not running the command and control server for this malware yourself, but it's like software as a service from the FlexiSpy authors. And this means they get to see all the data that you're gathering from a device unencrypted too. So this is another thing where you can see this is marketed at a consumer market. No serious intelligence operation would allow hosting the C2 software at a third party that also provides the malware. Whereas a consumer is very happy if he only has to set it up on the phone, and then it magically works by just surfing to a website and collecting the data from there. What you can see here is that there was a voice call. You can see the duration of the call, which contact was called, and so on. And then there's also location tracking being used here. So every now and then there was a new position of the phone being recorded. Now this is very, very simple stuff. And CrowdStrike, we're more interested in the more targeted attacks. And I want to start this off with looking at the Android malware that we saw in the wild, but maybe first compare this also a little bit to iOS. So what we see on Android is mostly regular applications or apps. So that means these applications are written in Java, and then using the Android SDK are compiled to a Delphic app. And that means they can be decompiled to Java as well. But often they're not even obfuscated. So that means that the original names of functions and class and so on in the Java source code are actually retained inside the app distribution that's being installed on the phone. So there is even public SDK tools to actually do this kind of obfuscation, to scratch these names from the apps that are on the phones, but they're not just not being used. So it's a very, very easy process to actually turn these apps from these DEX files, which is the packaging of apps, back into Java class files. And then from these Java class files, decompile into Java source code. So it's just like reading regular Java source code, which makes it very easy to reverse engineer them. And the question here is it really a visibility issue that we only see these very, very low hanging fruits, these very simple apps that are not obfuscated, just written in Java? Or is it just that this is a principle of least effort for the attackers, and just doing very simple apps this way is sufficient for them? And that's the question I want to talk about later too. On iOS, the targeted red ecosystem is largely unexplored. There's very few samples that have been observed in the wild. These commercial reds that I mentioned earlier are well known and documented, but that is not true for the targeted attacks. And we are pretty certain that this kind of attack is happening in the iOS ecosystem, but we have very, very bad visibility into the iOS targeted attacks. I'm going to talk about one example later, though. So first, as a case study for Android, I'm going to talk about Lucky Cat. So Lucky Cat in general, and the background behind it is it's a NATO group that engages in targeted espionage type of operations. So they're interested in collecting intellectual property and exploiting data, blueprints, and so on. So their main targets are engineering and research organizations and companies. They do, however, also target some political activists, so they don't have a clear mission themselves, but the majority of targets is in the engineering and research sectors. They are not only focused on mobile stuff, so they have like largely Windows malware for the desktop, and this has been attributed to Chinese developers actually. And the whole actor group is likely government-sponsored civil hacktivism. So it's civil hackers that are endorsed by the government to do this. And the group has been first seen in June 2011. There's actually a nice trend micro report on the Windows malware. But I want to focus on the Android malware here now. So the so-called LuckyCat.a samples was found on a C2 server for the Windows malware, which speaks about the operation security. The sample itself was not found on a phone in the wild. It was just that their open directories on the C2 server allowed researchers to actually download this Android malware, or rather download these files that were identified as Android malware later. So these Android malware samples are pretty simple. It's a very simple service-based app that registers for the so-called boot up intent, which basically means when you turn your phone on, the app is being started in the background. This is just a very normal way on doing this for any kind of service on Android. And then the service specifically reports general information about your phone as kind of a beacon on connection. So as soon as the app is able to connect out to the C2 server via TCP connection, it will report the phone number, the IMEI, so which is unique identifier for your phone, and so on, to the C2 server. And then besides this beaconing, it has the capability to read and write arbitrary files and list directory contents. This doesn't sound like much, but on Linux or on Unix in general, which is also true for Android, they have this philosophy that anything is a file, so you can access a lot of data and devices actually via this file reading and writing mechanism. And then a logic that handles these files that are being read is actually happening on the C2. So they could, for example, access the SMS database as a file and read it, but the parsing and so on is on the server side. So we only can see that they have the capability to access all these kind of files, but you cannot see just from looking at the red source code what data they're actually interested in. So they didn't implement specific commands for exfiltrating specific kinds of malware. And then, as is very typical with these custom rats, they have kind of a custom encryption scheme, which really is just an obfuscation scheme, but they call it encryption themselves. So looking at the beaconing, this is also a very nice example how easy it is to reverse this kind of targeted attack malware. We see here is basically the decompiled Java source code, which is not as nice as handwritten Java source code, but it gets pretty close and it's pretty easy to read. And as you can see there as well, they did not obfuscate any names. So these names like get phone number are actually from the original app and don't require a lot of reverse engineering to understand this kind of functions. As you can see there, this function is used to obtain the current phone number using standard Android APIs. And basically accessing data from the SIM card, which includes the phone number. And if it actually has problems accessing the SIM card, it will replace the phone number string with an error message string containing Chinese characters. And as part of the beacon, it uses in part this function to collect the phone number and then send it as a field in a GET request, which is actually called MAC. And this is related to the desktop malware, where this MAC field actually hosts the MAC address of one of the Ethernet controllers as a system identifier, but they just replaced this or repurposed this field in the mobile malware to use the telephone number as a system identifier. Besides only the phone number, it also contains the current IP address, which is interesting. You know, if you're looking at mobile networks, there's a lot of network address installation going on, so you can identify this and maybe spot if the person is using a wireless network or data network right now from the carrier looking at this IP address. And then they always include per incident identifier. This is kind of a case or file number for their attack that they're using to track their campaigns. So as I've said, it has only very, very basic commands to support accessing arbitrary files. And that comes very clear here. What you see here is basically a UML diagram of the malware. And in specific, we have these three functions here that access files. So there's mwrite file data fun, mread file data fun, and get directory listing or get to list. And these again are original names from the app that the authors choose. So the string fun in there is from them as well. So these functions allow the listing of directory contents and downloading and uploading files from the phone. Any interaction with the system at all must be done with a simple mechanism. So that means, as I've said, you can exfiltrate all kinds of data, such as documents, pictures, text messages, emails, and so on. But the more interactive kind of things, like doing calls, which would be interesting for doing a sound call to have a kind of a hot mic functionality, tracking GPS location, and so on. They're not possible using these simple mechanisms on Android. They would require using the Android binary IPC. So there's kind of a limitation, the capabilities of the malware here. And to take it from here to a little bit more advanced environment, I want to talk about some stuff in iOS too. I want to credit also Alex Radoshi, which is a colleague of mine at CrowdStrike, for conducting this reverse engineering with me. So what I want to talk about is FlexiSpy Mobile for iOS. FlexiSpy, or FinFisher in general, is a commercial solution that is sold to governments and specifically law enforcement agencies for monitoring whatever they define as criminals. And FlexiSpy Mobile is the mobile edition of this thread. It's kind of an enterprise software in that it has a proper development cycle, proper support, and so on. So this is solid engineering. And you can see that it uses proper encryption primitives like key exchanges, proper algorithms, not just some very easy XOR-based things. It has a properly designed communication protocol and so on. The sample that we looked at is actually provided by Citizen Lab, which is a stolen demo binary. So the official statement by Gamma International, which sells FlexiSpy or FinFisher, has been that the sample has been stolen from one of the demo servers. And this is exactly the sample that I will talk about. The capabilities of the thread are similar to the commercial threads that I talked about earlier. So they have the capability to track location, intercept on calls, and these kinds of things. But the key difference here is that this is not marketed at the consumer market, but marketed to law enforcement agencies, and as such, they will not run the C2 server for you, but actually provide you with a C2 software as well, so that you can run the entire operation in-house. And that's a key difference to these consumer market commercial threads. The iOS variant that I'm going to talk about requires a jailbreaking device or a local privilege escalation exploit. And that is basically due to how iOS is designed. iOS is a very secure philosophy in that applications normally aren't allowed to access all this kind of information that you want to exfiltrate with a RAT or access with a RAT. And there's two ways to circumvent the security mechanism, either by deliberately, manually jailbreaking your device, or by using an exploit to actually elevate privileges within the device. I'm going to talk about this now too. So first of all, how this is getting onto device. It's not very, very difficult. So there's one initial file, a Docker file, which is called the install_manager app, which contains the other components in its packaging. And this will drop these components onto the phone. So this application is assigned the ad hoc distribution certificate. Basically, in iOS, there are three different ways you can sign an application to be delivered and executed properly by an iOS device. There is a normal market distribution that everyone is probably familiar with, which means Apple will review your code and then they will sign it. And that means it can be run on any iOS device. But with the obvious drawback is that Apple will have to review your code first. Then there's enterprise distribution, which is not feasible for delivering RAD because it requires the installation of enterprise root certificates. And then there is ad hoc distribution, which is normally used by developers. And the big limitation in ad hoc distribution is that it requires hard coding, a so-called UDID, which is again specific to an iPhone or specific to a single unique device. And you can choose up to 100 of these UDIDs for one distribution package, one signed app, and it will only run on these specific devices. And requiring this UDID normally requires you looking at the phone and providing it. So it's really targeted, easy debugging for developers. In this case, the Install Manager app was actually signed with just a few UDIDs, and the certificate used for signing was registered to Mr. Martin Münch of Gamma International, which is their CTO, I believe. So attribution here is pretty clear, as in that Gamma International was cryptographically signed by Gamma International. This Install Manager app binary then drops the 4 main FlexiSpy binaries, and it does try to drop this to so-called SUID-able directories. So the set user ID property of a file basically means that when you execute the file, it will not run as a current user, but as the owner of the file, and typically this would be the super user, the root user. There's specific mounting options which prevent directories from containing such files, and when it drops these files, it tries to find directories where files can actually have these flags. So that means it wants to drop these files in a location where something can later set this flag on the files, such that when the files are executed, they're executed with super user privileges, which is the first hint. So talking about the four dropped files, this installer, which is only invoked by the Install Manager app, the dropper system infection, which takes care of making sure that the whole FlexiSpy binary application suite has some persistence in the system. So it registered is for startup launching. There's a login app wrapper, which is a very, very small wrapper that is just invoked by launchd on boot. Launchd is kind of what is in it on Linux. It's a process that launches different stuff that should be started when the phone is turned on. And it requires a special interface, which is implemented by login, which then in turn just starts the sync data app. So sync data app then is the main vector that calls home and provides the red functionality, data exfiltration, and so on. But there's also a trampoline app, which is in the sample that we were looking at, a broken null app. So it doesn't do anything. And yeah, those things in combination basically hint at the missing link, because to actually do this kind of data exfiltration, as I've said before, you either need to have an already jailbroken device or local privilege escalation exploit. So the installer app copies binaries, or attempts to copy the binaries to the /application and /system folders. And on a normal non-jailbroken device, this would be prohibited by the sandbox, by those directories being mounted read-only, and by not having the proper user privileges of writing to those directories. So that's basically 3 different protections that would normally prohibit this. The other thing is that the installer app requests root privileges with the set EUID, set effective user ID function. You can see that in the ARM assembly snippet in the lower right as well. And this behavior is very, very typical for a program that gets started with the set user ID bit that I mentioned before, because the real user ID will be root, but when you start sub-processes, normally they won't inherit the super user user ID for security purposes. And to make sure that your effective user ID, which is then also inherited by processes you launch and defines the behavior, is root as well, you need to in the program also request this by setting the effective user ID to 0, which equates to root or the super user. So you can see that the program itself, installer app, expects kind of behaving like a SUID-able binary. And then also install manager tries to find directories that contain SUID-able binaries. So everything looks like installer app should be SUID-able, SUID positive normally, but by default, of course, it cannot be, because you're not running as a super user on a non-jailbroken device normally. And this is where this broken no-op trampoline app comes into play. it is invoked by the install manager dropper that drops all these 4 binaries with the path to this installer app normally. So it's invoked by the dropper before the actual installer is invoked and pointing to the actual installer. And the code is, although it's broken and not doing anything, it still includes some snippets that build a full path to the install binary from the command line arguments. So it concatenates them to a proper path and so on. And then it just does this in stack buffers and then just exits. So it seems like it was just cut off or sanitized rather at the source level, or just a template binary that builds the correct path, and then after that you would add additional code. So this looks like a placeholder to disable the sandbox and to set the super user ID bit on the installer app. And basically, this means that this is an exploit likely to infect non-jailbroken devices. We looked very closely at Trampoline app if it's maybe a concealed exploit already. So there were cases where in previous jailbreaks they actually used properties of the loader and so on to turn a legitimate binary into an exploit, which wasn't obviously very obvious. But we looked very closely in the Trampoline app we were looking at. Definitely was not a local privilege escalation exploit and only a placeholder. Besides this analysis, recently there was also a much discussed UDID leak, and this has a different impact than only the privacy. So what was leaked? There was 1 million UDIDs leaked publicly, and that is these device-specific identifiers. Additionally, they leaked notification tokens for push notifications, and the device name, which also often contained the real name of the owner of the device. And this has been discussed as a privacy issue, but the other interesting property here is that proper code signing, so that your code can run and then elevate privileges on a non-jailbroken device in the first place. If you want to do this with ad hoc distribution, then you need to know the UDID of your target. And this is an interesting fact about this leak. So there has been, these UDIDs have now been leaked for 1 million potential targets, which allow to ad hoc sign malware or this kind of REST for those people. That doesn't mean that you automatically can just execute code. So still some degree of user interaction or exploitation is still required for deploying the binaries. And it will still be running on the sandbox, but it means at least that you can get a binary to run in the first place and get around the mandatory code signing. And you still need to have an exploit to elevate the local privileges, though. But this is the first step. It seems like actually the whole information was leaked from Bluetoad, which is an app development company, and there are certain indicators that point to this leak. So the original leaker said it was only from the FBI, but that does not seem to be true. So taking this all together shows you that exploitation on iOS is going on. That's very targeted at REST with a certain advanced degree of exploitation going on. And as the last part of this presentation, I want to talk about maybe an outlook for future advanced threats. So what is the reason why we did this feasibility study, basically? What we do know is that mobile exploits are being actively bought on the market, and they're bought for all kinds of mobile operating systems. This includes iOS, BlackBerry, and Android. People are buying both remote exploits for the baseband, for example, for the browser, and for SMS apps, and so on. So all kinds of different remote infection vectors. And people are also buying local exploits, and they're buying anything basically that gets you elevated privileges. So we do know that this is happening today. There is not a lot of publicity on these exploit markets, but these trades are being done as a matter of fact. And when you buy these exploits, then the development of the payload that you're actually installing on the device using one of these exploits is, of course, up to the customer that purchased the exploit. As an example, though, FlexiSpy Mobile looks like a very perfect fit for both containing a local privilege escalation exploit in the trampoline app, and also it would make sense to bundle this within a remote exploit to deliver it without the user noticing and without physical access to a remote target. So we know that these kinds of advanced threats are out there, but we don't have the proof or the conclusive evidence, right? So we are currently lacking an MD5 sum of a sample to say this is a sample that contains a local privilege escalation and is also red and so on. But it's very, very certain that these things are out there. So from our standpoint, it's basically a visibility problem. To quote our CTO, Dmitry Alperovich, if the mobile manufacturers don't give us root privileges, only attackers will have root privileges. And that basically is about the whole visibility thing. So as long as the manufacturers of these mobile devices and the developers and developing companies of the operating system that run there don't give us a means to efficiently deploy security monitoring software on such devices, we will remain with this very limited visibility. But we wanted to know, is it actually feasible to create such an advanced targeted threat for ourselves? So we tried to build this, and it's basically two things. First, there's an Android 4.0.1 browser exploit, which is exploiting a vulnerability in WebKit for remote delivery. The vulnerability has been fixed in WebKit 4.0.2, although it has already been public since November 2011. So this is not a zero-day, but still good enough to exploit pretty recent Android phones. Since the WebKit developers did not consider this a security critical issue, but just a bug leading to degraded user experience as in the browser crashes, no CVE was ever assigned. So the exploit that we developed needs to circumvent both XN and partial ASLR on Android 4.0.1. So what does this actually mean? Since Android 2.3 and later, Android activates XN, which is comparable to this NX bit on x86 or also on Windows called DEP, data execution prevention. So this is basically a bit in memory for different memory regions that tells the hardware if the data if this region of memory either contains data or executable code. And it will only allow to execute code within these code sections and not allow executing data. So when you're running an exploit and you're providing your malicious code, it will first arrive as data in the browser and will not be ready to be executed yet. Most of the phones actually do have hardware support for this specific bit, but it needs to be turned on. It's opt-in, and before Android 2.3, actually the Android did not activate this feature and therefore was more vulnerable. And then since Android 4.0, they added partial ASLR. ASLR stands for Address Space Layout Randomization. So it means that the different code sections that are legitimately in memory, because it's a code for the browser and maybe other code, are randomized. So they're not at a fixed position, so you cannot predict the location. What they did not randomize in Android 4.0 is the heap, the stack, and also the location of the dynamic linker. And this is pretty dangerous because the dynamic linker legitimately contains all the executable code that is also, from the perspective of XN, marked as executable code to load additional code that might potentially initially arrives at non-executable data, such as our malicious code that we're delivering in the exploit. And then later in Android 4.1 now, they added full ASLR, which means also the linker is randomized, and therefore you now need an information leak to identify the location of the linker. So what the exploit basically does is use return-oriented programming in the dynamic linker to circumvent all these mitigations and still execute code on the Android phone. And we coupled this with a native thread for Android. So native thread means it's a native standalone executable that just contains ARM, native processor instructions. It is not related to the Dalvik virtual machine. It's not built from Java source. It's actually programmed in C and then directly compiled into the instructions that directly run on the ARM processor. Normally, you would do this for performance reasons, so that the code actually runs faster, but it's also interesting for making it a lot harder to reverse engineer. So building such a native standalone executable using the Android native development kit is actually pretty easy, and that was one of the surprises for us. If you create a proper makefile, creating a hello world sample application for Android as native code for the first time takes less than 2 hours, if you're loosely familiar with the tool chain like GCC compiler and Make and so on. So there's this huge amount of these newly popping up app analysis experts that focus on the Delphic and Java VM, and basically their process is usually just decompose the Java source and then read Java sources. But of all these app analysis experts, has any one of those ever analyzed our native ARM code? And if so, if it's just simply packed with very, very simple UDID, which is a very widespread, legitimate packer, which also supports ARM, could any of these analysts unpack this if I simply scratch the static unpacking information? I doubt so. So if you do this kind of a native thread, you don't even necessarily need a rootkit on the phone, because people barely look at native processes on their phones. Native processes do not show up in Android or other third-party task managers because they don't, contain an app, and these task managers only list running apps. Even if you actually hook your phone up with USB to your computer, get a shell, and then do a PS process listing, it's still very trivial to obfuscate the process name with a native thread. So it's very hard to detect these native threads, even though if you don't have a rootkit that tries to hide them, because normally nobody just checks on their phone, right? So we built this demonstration, and you can look at the YouTube link that comes with the recorded webcast to see the demonstration. It's a very short demo because it just works so quickly. And it shows that it actually is very simple for a single person to develop such a very advanced attack. So it took me about 7 person-weeks to put all this together, and that shows that it's certainly feasible for a more motivated attacker to actually put this kind of an attack together as well, which means it's very likely that these attacks are out there for Android as well, carried out by intelligence services and so on, law enforcement agencies, and we just like the visibility into the whole ecosystem to just see them and provide, the evidence like this is the sample that does this exploit. So that's it about this last advanced threat part and the demo. Thanks for listening into the recorded demo.